We continue our study of the Lebesgue outer measure, and today we are going to learn some more properties of the Lebesgue outer measure. So the first one, I will put this as a lemma 1. This says that if E is a subset of Rd which is bounded, is an arbitrary bounded subset, then we have the following inequality which compares the Lebesgue outer measure M star E with that of the Jordan inner and outer measures. So we have already seen that the Lebesgue outer measure is bounded above by the Jordan outer measure, but it is also bounded below by the Jordan inner measure. So in particular, if E is Jordan measurable, then we have the equality of the Lebesgue outer measure with the Jordan measure of E. So this also holds for elementary sets, because elementary sets are Jordan measurable, and so with this inequality we can deduce, because if E is Jordan measurable, then these two things, the inner and outer Jordan measures, are equal, and so we have an equality with the Lebesgue outer measure of the Jordan measure. Okay, so let's try to show this result. So we already know that M star E is bounded above by the Lebesgue by the Jordan outer measure. So we have to show that the Jordan inner measure is bounded above by the Lebesgue outer measure. First note that M star of E is finite because E is bounded. So if E is bounded, then the Jordan outer measure is finite. We have already seen this. So in particular, the Lebesgue outer measure is also finite. So given epsilon greater than 0, we can find a collection Bi I equal to 1 to infinity of boxes in Rd such that we have M star of this sum I equal to 1 to infinity M star of Bi, rather M of Bi, is less than or equal to M star E plus epsilon. So this is from the definition of the Lebesgue outer measure, from the definition of the Lebesgue outer measure. Now take any elementary set F inside E. So we will show that the elementary measure of F which sits inside E is bounded above by M star E plus epsilon. So one can then take the supremum on the left hand side and we get, so the inner Jordan measure F elementary MF is then bounded above by M star E plus epsilon, and because epsilon was arbitrary we would be done. So we have to show this inequality, that MF is bounded above by M star E plus epsilon. So to prove this we need the following fact from topology, which is called the Heine-Borel theorem. So we recall it here. It says that every closed and bounded subset of RD is compact. Compact meaning that every open cover has a finite subcovering by definition. So this result is a deep converse for the fact that every compact set in RD must be closed and bounded. So this is a converse saying that every closed and bounded subset is also compact. So we would need this fact. So let's see first how we will apply this. So suppose that this covering that we used, bi equal to 1 to infinity, used to cover E is made up of, consists of only open boxes, So to apply the Heine-Borel theorem, which is to apply compactness, we would need the covering to be open. So that's why we are supposing that each of these box bi is open. Suppose also and that F is closed, is a closed subset of RD. So because E was bounded, if F is closed, F is also bounded. This implies that F is compact, and so F is covered by the union of these boxes bi's, and each box is open in RD. So because F is compact, there exists a finite subcover of these open covers bi, I equal to 1 to n, so up to reordering, up to re-indexing. So if needed, we can re-index this collection bi, and we can take all the needed boxes, open boxes bi for this subcover, finite subcover, and arrange it from 1 to n. So we can write that this finite subcover is the collection bi from I equal to 1 to n. And so the measure of F, so of course the finite subcover means that F is contained in this finite union of boxes of bi I equal to 1 to n. So this implies that the measure of F is bounded above by the finite sum from I for I equal to 1 to n m bi, and this is bounded above by the infinite sum, because we have only non-negative values, so we can extend this sum to the infinite sum I equal to 1 to infinity m bi, and this is then bounded above by m star e plus epsilon. So if F is closed, and if these bi's that are used to cover E consist only of open boxes, then we can immediately find our required inequality, which is MF is less than or equal to m star E plus epsilon. But because this is not always the case, so we have to do some more carefully we have to investigate a little bit more on how to reduce it to this case. So suppose first that F is closed, but the collection Bi I equal to 1 to infinity covering E such that this sum I equal to 1 to infinity MBI is less than or equal to M star E plus say epsilon by 2. So we can choose such a collection of boxes Bi, countable collection covering E such that the sum, the infinite sum is bounded above by M star E plus epsilon by 2. Now for each I greater than or equal to 1, choose an open box Bi prime such that M of Bi prime is less than or equal to M of Bi plus epsilon by 2 to the power I. So again we are going to use the epsilon by 2 to the power k trick because we want to sum it up in the end. So there is an epsilon by 2 to the power I, and this is an interesting exercise in its own. Exercise, justify that such Bi prime exists. So here it's a matter of enlarging the box Bi such that the volume of the enlarged open box Bi prime is very close to the original volume of the original box Bi up to some epsilon. So in fact one can choose any arbitrary epsilon and one can still find an open box Bi prime such that Mbi prime is less than or equal to Mbi plus epsilon. That's all we need to prove. So it's an exercise which I leave to you to justify that such Bi prime exists, such open boxes exist. So given this implies that sum equal from I from 1 to infinity Mbi prime is less than or equal to sum I equal to 1 to infinity Mbi plus we will have an epsilon, extra epsilon here. So let me write here 2 to the power I plus 1, so we will get epsilon by 2. So this epsilon by 2 and the epsilon by 2 above are going to give us epsilon. So now we have a covering of E by these boxes Bi prime, and each Bi prime is open. So since F is closed, we are back to the previous result that we showed. So this implies that Mf is less than or equal to M star E plus epsilon. So this shows that when we assume F to be closed, but Bi's can be an arbitrary collection of boxes, then we can enlarge each of these boxes, keeping the volume, keeping control over the volume of these boxes, such that in the end we have a collection of open boxes and we'll still get the result that we want. Now we still have to prove the case when F is not closed. Now suppose that F is an arbitrary elementary set, elementary subset of E. So this implies that there exist boxes. Let me write this as AKs, k equal to 1 to capital N, such that F is equal to the union of these AKs, k equal to 1 to N. So we can also assume that these boxes are disjoint. So our MF is equal to the sum of these measures MAKs, k equal to 1 to N. So we have an arbitrary elementary set F, which is then expressed as a finite union of disjoint boxes AK. Now we are going to replace these AKs by closed boxes such that the measures don't change too much. So for each k greater than or equal to 1, so k between 1 and n, choose a closed box AK prime inside AK such that we have the measure of AK prime is greater than or equal to measure of AK minus epsilon by n. So for each k we are choosing a closed box, sub box of this box AK, which we denote by AK prime, such that the volume of this smaller box is between is greater than or equal to MAK minus epsilon by n. So again it's an exercise to justify that such AKs, AK primes, exist. So in the previous case we used an enlargement of an arbitrary box to an open box, and in this case we are going to shrink the boxes a little bit so that it becomes a closed box, but still we have control over the volumes. So now this implies that the sum k equal to 1 to n m a k prime is greater than or equal to the sum k equal to 1 to n m a k minus, we will get epsilon because there are n terms, so we will just get epsilon. So the right hand side is nothing but mf minus epsilon. Now for the closed elementary set f prime, which is the union of these AK primes, k equal to 1 to n, we get m of f prime is less than or equal to m star e plus epsilon, because we have already shown that when we have a closed elementary set, then this inequality is satisfied. So for the closed elementary set f prime, we can write this inequality, and m of f prime is then bounded below by mf minus epsilon. So this implies that mf is bounded above by m star e plus 2 epsilon. But since epsilon is arbitrary, epsilon was arbitrary, we get MF is less than or equal to M star E, and finally this implies that the inner Jordan measure is bounded above by M star E, which is bounded above by the outer Jordan measure. So finally we have proved what we wanted, which is that the Lebesgue outer measure is sandwiched. So this is the Lebesgue outer measure. It is sandwiched between the Jordan inner measure and the Jordan outer measure for bounded subsets of RD. So in particular, when E is Jordan measurable, then the inner Jordan measure and the outer Jordan measure coincide, and they will give you the same result as the Lebesgue outer measure. So one corollary is that the set given epsilon greater than 0, the set U epsilon, which is equal to the union I equal to 1 to infinity Q I minus epsilon by 2 to the power I plus 1 Q I plus epsilon by 2 to the power I plus 1. So where Qi I equal to 1 to infinity is an enumeration of the countable set of rational numbers inside 0 1. So we have seen this argument, we have seen this example before where I claimed that this is not Jordan measurable, and we will prove this here. So now we can compute the Lebesgue outer measure of U epsilon, and this is less than or equal to the sum of epsilon by 2 to the power I equal to 1 to infinity, and this is just epsilon, right? And the Jordan outer measure of U epsilon is equal to the Jordan outer measure, it's greater than or equal to the Jordan outer measure of 0 1, since 0 1 is a subset of U epsilon because the rationals are dense in 0 1. The set 0 1, the interval 0 1 is a subset of U epsilon. So we have by monotonicity that the outer Jordan measure of U epsilon is greater than or equal to 1, while the Lebesgue outer measure is less than or equal to epsilon. So since the inner Jordan measure is less than or equal to the Lebesgue outer measure is less than or equal to the Jordan outer measure, this is bounded above by epsilon, while this is bounded above by 1. So if you choose epsilon small enough, so if epsilon is strictly less than 1, then this shows that U epsilon is not Jordan measurable. So this is an example of an open bounded set. So this is an open bounded subset of R, which is not Jordan measurable. This also shows that the following fact, that, so I put it as a remark, that countable unions of Jordan measurable sets may not be Jordan measurable. So we mentioned this before, and with the help of the Lebesgue outer measure we have shown that countable unions of Jordan measurable sets may not be Jordan measurable. In this case, our example was this open set U epsilon, which was a countable union of intervals k equal to 1 to infinity qk minus epsilon by 2 to the power k plus 1 qk plus epsilon by 2 to the power k plus 1. So each of these is Jordan measurable. This is just an interval, so it's a Jordan measurable set, but the union is not Jordan measurable even if the union is bounded. So in this case the union is of course bounded even if the union is bounded. So one could have unbounded unions, but their Jordan measurability is not defined yet, but even if the union is bounded, we have shown that it may not be Jordan measurable. So this is the first one. Second one is that closed bounded sets may not be Jordan measurable. So we can take, for example, f epsilon, which is the complement of u epsilon complement intersecting with some big interval, let's say minus 3 to 3, and this set is not Jordan measurable, because if it was Jordan measurable, so it's not very difficult to see that f epsilon is not Jordan measurable for epsilon small enough, of course. Since if f epsilon was Jordan measurable for all epsilon, then you can take the complement of f epsilon, which would then be Jordan measurable if you intersect it with say minus 3, 3. Now this will be a Jordan measurable set, but one can show that this is nothing but u epsilon. So this is a contradiction. Then would be Jordan measurable. This is a contradiction. So f epsilon is not Jordan measurable. So we have seen that open bounded sets as well as closed bounded sets may not be Jordan measurable. Now we come to our next property, and to state this property we make the following definition. If E and F are subsets of Rd, arbitrary subsets, then E and F are called almost disjoint if the interior of E is disjoint with the interior of F. So here E interior, E, I am using this notation, is the interior of E, and similarly for F. So almost disjoint means that once you take the interior, remember that the interior is the union of all open sets U inside E. So once you take the interior and of E, and once you take the interior of F, then you get an empty intersection. So the following lemma uses the concept of almost disjoint sets. So if E is a subset of Rd, is a collection, is a countable union of almost disjoint boxes, then the Lebesgue outer measure is given by the sum I equal to 1 to infinity. So let me write Bi to be this collection I equal to 1 to infinity, to be this collection of almost disjoint boxes. Then the Lebesgue outer measure is the sum I equal to 1 to infinity m of Bi. So here note that if B1, B2 and Bn is a finite collection of almost disjoint boxes, then the measure of the union of these Bi's I equal to 1 to n is equal to the sum of these Bi's, because since measure of the interior of Bi is the same as the measure of Bi. So this lemma extends this fact to countable union of almost disjoint boxes. So let's try to prove this. Proof is not very difficult. So first we note that the outer measure of E, so E here is, remember, the countable union of these boxes which are almost disjoint. So by countable subadditivity we get that the Lebesgue outer measure of E is bounded above by the sum of the measures of these Bi's I equal to 1 to infinity. This is from countable subadditivity. So it suffices to show, that the reverse inequality, that the sum is bounded above by m star E. So this is pretty easy. So for example, if you can take any finite collection, take any finite collection Bi I equal to 1 to capital N, okay, for some n in the natural numbers, then the union I equal to 1 to n of Bi's sits inside this set E. So by monotonicity we have that the measure of this set is less than or equal to m star E, but this is the same as the sum I equal to 1 to n measure of Bi is bounded above by m star of E. Now you can, so this is true for all n, this is true for any n in n. So we can take the limit, as n goes to infinity on the left hand side. So we get the limit n goes to infinity I equal to 1 to n m Bi is bounded above by m star E, but this is nothing but this infinite sum by definition of an infinite sum. We get the required bound. So as a corollary of this result, it can be shown that if E is a countable union of almost disjoint boxes which is also bounded, then the Lebesgue outer measure is equal to the inner Jordan measure of E, because both of them are equal to this sum, I equal to 1 to infinity m of bi, where E is this union of bi's. So of course we have shown that the Lebesgue outer measure is equal to this sum. To show that the inner Jordan measure is also equal to this sum, we can again apply that these finite unions are equal to 1 to n. So this is now an elementary set. This is an elementary set, and so this is contained in E, and so the the Jordan measure of this set bi is less than or equal to the inner Jordan measure of E, and this is nothing but again I equal to 1 to n mbi, because this is an elementary set. So we can remove the inner Jordan measure, it's just the elementary measure, and so this is bounded above by E, and then again you can take the limit as n goes to infinity. So this is the idea of the proof, which is the same, essentially the same as the lemma before. So we see that the inner Jordan measure for a countable union of almost disjoint boxes which is bounded is then equal to the Lebesgue outer measure.